of the Lambert transfer code that has been updated in Gravity Engine 2 in release 5.0. This all started with a desire to move the computation of transfers into the job system, especially for pork chop plots where you compute a whole slew of Lambert transfers. Yeah, I know I should be saying Lambert, but that's not likely to happen. And in doing so, I discovered that my favorite astrodynamics book, Viato, had an updated version of the algorithms, more or less the same algorithm as in Gravity Engine, but with a few enhancements, which I'd kind of anticipated in Gravity Engine to handle 180-degree transfers and so on. If you want to delve further into the math behind Lambert transfers, Viato points you to a very lovely description in Pressing and Conway, which is a great book if you can disregard the price. And then there's also some cool stuff on calculating Lambert transfers using flight path angle instead of time between the points in this book. This book, Methods of Orbital Maneuvering, which is a quite recent book by DiPrinzio. And there's lots of good stuff in here, some of which will find its way into Gravity Engine in the future. So let's start with the basic idea of a Lambert transfer. So to begin with, I've put all of this stuff in the Tutorials Going Further LambertInDepth folder. And it seems like there's a lot of scenes here, but in some cases it's just because I do the same thing in all three unit systems, so dimensionless, SI, and Earth orbit scale. So let's start with the basic Lambert explainer scene. So we'll go there. Now, the key inputs to a Lambert transfer are 2 points, R1 and R2. And the goal is to find a curve through those 2 points that is a gravitational trajectory around the mass in the center. And there's more than one. There's a whole family of conics that go between these 2 points, and we can go through a variety of them. And so we need to discriminate between these paths in some way. And so the conventional way to do that is by specifying the time you want the transfer to take between the 2 points. As I mentioned, it's also possible to say what direction you want your new velocity vector to be in, which would be specifying the flight path angle. And that's another way to discriminate between these families of points. There's another thing to consider, which we can look at in the short versus long scene here. So between these 2 points, for a given time, we could go either way. Both of these are valid solutions, one of which assumes you want to go through this short, it's called the short path because the angle between the points is less than 180 degrees, and the other is called the long path because the angle between the points going clockwise around this way is greater than 180 degrees. Typically, if you're this body on the right that you're starting from, you do not want to go backwards because that is a huge dV. So most of the methods in the new Lambert class will prefer to go in the prograde direction, i.e. don't go backwards. And those all have a prograde phrase in their API name so that it's very clear to find those. So now that we have those in hand, note that when we have talked about this so far, we've talked about 2 points and either the time between them or the flight path angle, but we haven't said anything about the change in velocity required to do this transfer. And generally, when you're dealing with spaceships, you want that change in velocity to be as small as possible. That's sort of not the input to the Lambert algorithm. To find that, you have to actually do a little bit of a search along the various choices of time or flight path angle to find the minimum dV. So to make that easier, in Gravity Engine, I've now created, and let's look in the hierarchy here, this thing called the Lambert Flight Path Angle Planner, although it will also do time. And if we just go ahead and start this scene, you'll get an idea of what's going on. So we have in this upper right corner this handy graph of what flight path angle will give us the minimum dV transfer. And in this case, we're going from one point to another point. We're not worried about matching the velocity of some target object. And we're not worried about whether the point we're going to is going to move while we're moving. We can talk about that in a second. But this is just the simple case where we're starting at a point and we're trying to get to a destination point. And there's some sliders at the bottom that we can change. There are also two reference curves which can be useful when you're trying to get a handle on what constraints to put on the search you're using to find a minimum dV. There's a minimum energy conic that goes between the 2 points, and that's the curve shown in green here, and that has a particular time. And then there's a parabola, so the curve that has eccentricity 1, and that's given by the red line here, and that has a reference time. You would generally not want to go in as short a time as the parabola says. You would probably want a time more typically like the minimum energy time. But in fact, in this particular example, the time that has the minimum energy is longer than the 38 time units. It's 52 time units. When this scene starts, it starts with the marker at the minimum energy. If you want to look at examples of how this changes, you can change the flight path angle by dragging the flight path slider, or you can drag the transfer time slider. And you can see how you move along this curve. This is a curve of flight path angle. If you want to look at the curve of time, then as the comment says up here, if you just hit T, you can flip to something of time, and then you can go back and find that minimum again of 0.24 at about there. So this is a really nice way to visualize. These reference curves for minimum energy are useful because in a given orbital situation, it can be kind of hard to sort of come up with what's a reasonable guess for a transfer time. If this scenario works for you, that is, you don't care about the moving target, flight path angle is really great because you very seldom would want an answer that's sort of outside of the 45-degree forward cone of your spaceship. And so that gives you a really nice constraint on the search space here, where you can go back and forth. Just one little subtlety, if you go too far where your ellipse becomes a hyperbola, if we go way up here, then you have no choice but to go in the reverse path because you can't go out to infinity and come back from infinity on the hyperbola. That's what's going on, just in case anybody notices that. Now, in reality, what's a more likely scenario is you're not trying to go to a fixed point in space, but you're trying to go to some target that's also in orbit around the center body. So there is a target planner, and we can start that. And in this case now we only have a time of flight slider. And notice that the longer we take, the further along the outside orbit our target moves. And so we have to be aware of the fact that as our transfer time changes, the position of our target changes. And that's what happens with this scenario. So if we want a short aggressive transfer with higher dV, we can be up here on the curve. If we want to be kind of down in the flat part, these are both circles, but of course all of this works with arbitrary shaped initial and final orbits. The circles are just convenient to show here. And then if you want to, in this scene, you can just hit X, and then the transfer will just go ahead and be put into the GE core, and you can see that we will get to the target position and then match that orbit. Now this planner, we'll just start it again, assumes that the initial position is fixed and you want to start right now. But it might be the case that a more efficient transfer involves waiting perhaps a quarter of or 2/3 of an orbit before initiating the transfer, because then the phasing with the target object would be more advantageous. And so what you really now want to do is a two-dimensional search where you say for different departure times and different arrival times, what is the dV? And so that's what is called a pork chop plot. because the resulting kind of contours you get reminded people of the shape of a pork chop. And so this is now done in Gravity Engine 2. There's a Lambert job system that will go ahead and under this controller, we'll just go to this one and look at the hierarchy. You can see there's a Lambert to target pork chop. I won't in this video go through all of the details of the parameters for setting up the pork chop. That'll be in the reference documentation, but it's generally expressed as a fraction of the ship's initial orbital period, because then we don't have to worry about absolute time units, so we can make everything kind of relative. So this one is actually based on a Earth-Mars transfer with the Earth-Mars positions taken from 2018. And if we go ahead and press play, there's kind of a lot going on here, but you can see there's a sample curve, and you can see there's a little ball here that's found the minimum transfer time. So there's a particular departure time in the future and a particular arrival time, and then the transfer takes that delta. And then you can see that the DV has been color-coded, and in fact it's been color-coded with the log just to add a little bit of dynamic range. That's all selectable in the options of the controller. And then you can click, there's this thing where it zooms out. You can click at different points on the pork chop and see what the different choices look like. And then if you want to, you can hit X and start the transfer off. And it'll wait until it gets to the appropriate time to start the transfer. It'll go ahead and start the transfer. And then when the bodies get to the same point, it will match. Now, it's important to understand one subtlety when you do this Earth-Mars example. This is a pork chop plot as if your ship was in the same orbit as Earth and wanted to be in the same orbit as Mars at the end. It doesn't yet include the patches needed to escape the Earth's gravitational field and arrive into the Mars gravitational field. That's something that will be coming in a subsequent release. The way this is set up, if you look at, for example, a LEO to GEO pork chop, then the to and from are actually exactly the kind of thing you need. And you can find out what kinds of transfers you might want to have for LEO to GEO, your various choices depending on where you click. And again, it shows you the DV. The other thing that the documentation explains, if you look in the here, you have some choices about what kind of DV to plot. You might be interested in the departure total velocity, or the DV at departure, or the DV total, meaning you care about how much of a correction you have to make when you arrive at the final orbit. Generally speaking, DV total is probably the most interesting one, but there are some choices to be made there. All of the details for how these controllers work is in the documentation. There are a bunch of fields and modes required to set up. The Lambert transfers themselves are all contained in a new piece of code called Lambert, and it is all stateless, and it all is all struct based, and that's so that when you want to do things like batch a bunch of pork chop calculations onto a Unity job, that is all relatively straightforward. There is a Lambert job wrapper that allows you to basically give it a vector of a whole bunch of input conditions you want to compute transfers for, and then the job will go away, do all of those, and then when that job completes, you can go grab the data. If you delve into the code of these various controllers, you'll discover how that all works. I think this is a pretty good step forward for Gravity Engine 2, and I look forward to adding more features, including the patched conics for planetary transfers. Thanks for your attention.